All right, we have Marco Vincentelli from Colombia. He's going to continue his lectures on degenerate automorphic forms and Euler systems. Over to you, Marco.
Thank you so much, Shanak. Today's talk, as I said yesterday, I'm gonna treat in some detail the example of the Euler system we construct with Chris for rho is the adjoint representation of the Galois representation coming from a cuspidal eigenform on GL2. So the important pair of groups, let me recall it that it was GL2 times that GL2 inside GSP4, or really maybe more simply SL2 times SL2 inside SP4. So the plan for today's lecture is going to be, first I will talk about holomorphic Siegel-Eisenstein series. And then I will talk about compactifications of the Siegel threefold. And which are key in understanding what the properties of these Eisenstein classes are. And then I will talk about what is known in the literature as the Manning-Drinfeld principle. And lastly, so I will conclude to say the upgrade of the analytic classes to geometric étale classes with known Galois action. So I will probably won't have time to go a lot into details, but all the main ingredients will be explained here. Okay, so this talk will be about really the main ingredients that come into play in proving the properties of the classes. Okay, so let me start with one. So Siegel-Eisenstein series. And so there are a lot of parallels with respect to the GL2 case. So in green, I will write down the GL2 case, like the parallel case. Okay. Just so that to give you intuition about what the analogs of the objects that I will define in the Siegel case are in the GL2 case. So first of all, let me introduce the analog of the upper half plane. So I will denote by H2. These are the set of matrices, 2 by 2 matrices Z1, Z2, Z0, Z0 in M2 of C, such that the imaginary part of the matrix C is positive. And so compare with respect to the GL2 case, where H is just the upper half plane. So these are the tau in C with positive imaginary part. Okay. And so on this, so for a matrix Z in the Siegel upper half space of dimension 2 of genus 2, we can consider for an odd Dirichlet character chi, consider the series. So E chi of Z comma S, which is going to be the sum. Here I will say what the prime means over 2 by 2 matrices C and D, which verifies some concurrent conditions of that of C. And then here we have that of CZ plus D minus 3, and then the absolute value of that of CZ plus D to the minus S. Okay, so the sum is over pairs C of D of 2 by 2 matrices such that the following holds. So C times D transpose is symmetric. So symmetric with coefficients in Z. So both C and D are 2 by 2 matrices with coefficients in Z. And C times dt is symmetric. And N divides D, where N is the conductor of chi. And C is non-singular mod N. And so the analog in the GL2 case is f chi of tau S, which is just the sum over pair CD of chi of C, and then here just CZ, so sorry, C tau plus D to the minus 2, and then CZ plus D to the minus S. So the usual series defining the GL2 Eisenstein series. Okay, so now this series converges for the real part of S greater than 0. And here, since we're in weight 3, one can show that there is no pole and it has an analytic continuation. A continuation in S, so for fixed Z, and no pole at S equals 0. So you can define by Hecke summation E chi Z as E being equal to non-absolutely convergent series that I will write down as chi of that C of that of CZ plus D minus 3. So this is my Siegel-Eisenstein series that I will be interested in. This is what I call the Siegel-Eisenstein series. And this is a holomorphic function in Z on the Siegel upper half space of genus 2. Okay, and so, and the same process happens in GL2. It's just that since here we're, if I'm putting weight 2 here, then chi would have to be even, as in Chris's talk. Okay, and so now I will denote by G. I will take the sort of automorphic point of view on E chi of Z. So G is as before. P, let me say that is the Siegel parabolic. So for an appropriate model of, for appropriate basis of the defining representation of SP4, this can be considered as the set of 4 by 4 matrices that are of this form, where A belongs in GL2. So the Levy is isomorphic to GL2. And this star here is a symmetric 2 by 2 matrix. So the unipotent radical is isomorphic to 2 by 2 matrices. So in particular, it is abelian. It will be important later. And so now I introduce what the level structure of E chi Z is. So I will denote by gamma 1 of N. So N, recall, is the conductor of chi. So this is just the set of matrices M in G of Z, such that M is congruent to A transpose minus 1, and then something 0 mod N, and that of A is congruent to 1 mod N. Okay, so then you can consider really E chi Z rather than just as a function on H2, more as a differential, as a 3 form. You can consider E chi Z times dz, where dz, if my coordinates on the Siegel upper half space were z1, z2, z0, this is just dz1, dz2, and dz0. So This I will denote by omega chi. This differential, this is a differential on H2, it's a 3 form, descends, because it's invariant under the direction of gamma 1, descends to, so M1 of n, which is H2 mod gamma 1 of n. Okay, so then this means that omega chi, you can really view it as a global section of the 3 forms on M1 of n. And this, I view it, I can see that the Durham class, I can view this inside the Durham cohomology of M1 of n. And let me stress that this is over C, because, so these M1 are the complex points of an algebraic variety that's defined over C. Okay, so yeah. Sorry, I mean, since I've taken SP4 over an abelian extension of Q, but it's the complex points of an algebraic variety defined over a number field, the Shimura variety for SP4. Okay, and so let me just state what the parallel for GL2 is from Chris's talk. So in his talk, he had f chi of tau d tau, which descended, is a 1 form on H, and descended to a section of y1 of n, and then omega 1 of y1 of n. Okay, so as of now, we've just interpreted an explicit Siegel modular form as a differential on a complex algebraic variety. So maybe let me give now, with respect to yesterday's talk, the representation theoretic interpretation of this modular form. So representation theoretically, so E chi z can be viewed as a vector, a holomorphic vector in the representation. That is the normalized induction. So pi chi, the normalized induction from the Siegel parabolic to G of A of the modulus to 1/2 times chi composed with the determinant, where chi is the same character as before. Okay, so this is my family of degenerate automorphic forms. And let me also stress that yesterday Dipendra Prasad made a good point that, you know, usually people in automorphic people call, you know, degenerate Eisenstein series that are induced from a character of the levy of the parabolic, and this is also degenerate in that sense. Okay. And so let me again state the parallel for GL2. In the case of GL2, then we would consider this induced representation of, so delta of the Borel to the 1/2 times chi, okay, where chi would be even. Okay, so in the rest of the talk, so the aim of the rest of the talk is try to understand the arithmetic properties, or more maybe geometric properties of omega chi, which was my E chi z dz. So, and that from the point of view of yesterday's diagram, so recall, so yesterday's diagram, so now I'm giving what all the terms are. So I had my family of p chi, then this arrow here had the p-adical function for at the row. And this was done by Zheng Liu, the construction of the p-adical function from the family of p chi's. And now we've done the first step, which is analytic de Rham classes. So these are my omega chi's. So this is specialization to classical point. So this is just the specialization of the family that's underlying these EKZs to weight 3, and so this EKZ. So this gives me an analytic de Rham class, omega chi. And now in this talk, I want to explain a little bit. So this arrow, so upgrade to et al. Classes, omega chi et al. With known Galois action. This is this talk. Okay, so we've done the first step, which is rather simple. There is no secret. And moreover, we also want to see that the comparison between et al. And the Rham cohomology by Faulting-Strugi of omega chi et al. Is very closely related. So actually equal, related to the p-adic modular form associated to EKZ. So here there is a slight lie. So in this series, that I defined, there is always this. So here there is a normalizing factor that is used so that the Fourier coefficients are algebraic, etc. So this is possible. I will, ignore this this fact. So you want to relate at least locally, the local de Rham class to the p-adic modular form that's underlying EKZ. Okay, so and this will be done in next talk because it's closely related to the integrality properties of omega chi et al. So in this talk we will only define a class. So in the et al. Cohomology of M1n, but with coefficient in QP, actually QP3, but okay. So, and in next talk, we will upgrade QP to ZP. Okay. So the key to the upgrade, is to understand why, sort of geometrically, the parameter of pi chi is small. So it's degenerate. So this is small because, in this case, because it's induced. So Eisenstein series, in the case of Eisenstein series, of course, they only exist if there are rational parabolics. So if exist if there are parabolic subgroups. So this is closely related, of course, to the fact that the Shimura variety of G, so the group where the Eisenstein series, let's say on G, is non-proper, is non-compact. And so it should be that Eisenstein series, Eisenstein classes come from the boundary, which is precisely controlling the non-compact nature of the Shimura variety for G. Okay, so so this leads us to study the compactification of Shimura variety and see how these Eisenstein classes arise from this presence of the boundary. So this leads me to number 2. So compactifications of the Siegel threefold. Okay, so unfortunately, there are many compactifications and each one of them is important in this theory. So let me introduce the relevant notation. So from now on, I will denote by Y is my M1 of N. And so 4 useful compactifications. So here I have Y, which injects into, say, toroidal compactifications. This depends on some auxiliary choices, but I will not explicate them. So toroidal compactification, and then which maps to the Bailey-Borel compactification, also known as minimal compactification. But crucial in this talk will be really what is called the Borel-Serre compactification, which also map to the what is called the reductive Borel-Serre compactification, which then map to the Bailey-Borel compactification. Okay, so these are the 4 compactifications: Borel-Serre, reductive Borel-Serre, Bailey-Borel, and toroidal compactification that we will need. Let me just try to organize them and say that this side, the bottom arrow, is where the compactifications are algebraic. So this one is smooth, but this one is singular in general. So in the case of Siegel theory, it is singular. So let me just say singular. Okay. And these ones, so maybe let me use another color. These ones are just topological, meaning real manifold with corners, so even singulars. Okay. So now let me try to explain what each role of these compactification is. So the key role in this talk is that the key property, YBS, the Borel-Serre compactification of Y, retracts onto Y. So the Betty homology of Y is the same thing as, with say coefficient in C, is the same thing as the Betty homology of YBS. So this allows one to see the contribution of the boundary to the homology. So because then the relative homology sequence with respect to the boundary. So let me denote by delta BS the boundary. So YBS without boundary. So you have an exact sequence where the homology of YBS maps to the homology of the boundary. And the kernel is just so this is +1 degree. So it's just the Betty homology with compact support of Y. But this is just H star of Y. So really, this equality is given by pullback under the inclusion. So this I call iota of BS. Okay, so this allows you to examine what the contribution of the cohomology of the boundary is to the cohomology of Y, which is sort of the crucial point when you're trying to study Eisenstein classes. So now what is the role of Y Tor? Well, it's because there it's where naturally the Q expansion of Siegel modular form is defined. And so it controls integrality, integral structure of coherent cohomology, which will be crucial for us to prove integrality of ZP integrality through integral periodic Hodge theory. So Y-Tor also plays a very important role. Then maybe the smallest role that is played in this story is by the reductive Borel cell computation, compactification, but this is actually used in computing, well, the cohomology of the boundary of the Borel-Serre compactification in terms of induced representations of uh, um, in terms of a cohomology of locally symmetric spaces of levies of parabolics of G's, parabolic subgroups of G. Okay, so this the reductive Borel-Serre compactification plays some sort of auxiliary role. And lastly, but not least, the Bailey-Borel compactification allows one to understand the Galois action using results of pink. Okay, so I won't, this unfortunately, I don't think I will have time to comment much on this point, but basically, since the Borel-Serre compactification is not algebraic, it doesn't really make sense to talk about the Galois action on the boundary of the Borel-Serre compactification, but it does on the Bailey-Borel compactification. And so one of the key technical points at some point to understand the Galois action on the class is to replace the Borel-Serre compactification with the Bailey-Borel compactification. Okay, so maybe let me state in the case of GL2 who this compactification are. So this compactification exists for general Schimuren varieties or really locally symmetric spaces. So so in the case of GL2, so YBB is just X, the usual compactification, by adding the cusps. But this is also the reductive Borel-Serre. And then the Borel-Serre compactification is Y disjoint union S1s for each cusps. One circle for each cusp. So when Y, say it's Y1 of n. Okay, so and so the picture of Y Borel-Serre to Y reductive Borel-Serre is just a circle mapping to a point, okay, on the boundary. So on the boundary, so delta Borel-Serre mapping to delta reductive Borel-Serre is just a circle mapping to a point. And of course, on the open locus where you're on Y, it's just the identity, okay? So this was the case of GL2. Now let me actually go to describe a little bit what the case of the Siegel threefold is. So the boundary delta BS has components indexed by GQ conjugacy classes of parabolic subgroups. So in this case, there are three GQ conjugacy classes. So as I said before, P is the Siegel parabolic, then Q is the Klingen. So this is 4x4 matrices that are of this form in the same model. And then I have the Borel. Okay, so I will mainly focus on the boundary component attached to conjugacy to the Siegel parabolic. And let me just state that, so usually, so not usually, always, so if star is always in P, Q, or B, delta star BS is the component corresponding to this conjugacy classes, and there are closure relations. So for example, the closure of the one attached to the conjugacy classes for P is the one for P, disjoint union, the one for Q, for B. And the same thing for Q. B delta BS, and the stratum for B is closed. So there are general formulas, but to understand what the closure is, but in this case, it's just this. And now in general, we've done the case of GL2, but so if you're looking at the boundary of the Borel-Serre compactification mapping to the boundary of the reductive Borel-Serre compactification, this is what is called a Neal manifold fibration, meaning at each point the fiber possesses a transitive action of a nilpotent group, and by the Serre fibration spectral sequence, this allows you to compute the cohomology of each boundary component in terms of the cohomology of the Lie algebra cohomology of this nilpotent group, valued in some sheaf coming from the cohomology of the reductive Borel-Serre compactification, where this is just a union of S of M star. So where S of M star is a locally symmetric space attached to the levy of star. So star, recall, is P, Q, or B. Okay. So this allows you to compute the cohomology of the boundary in terms of the cohomology of the levies and an induced representation. So let me say what this is in the case of the boundary component for P. So if P, so let me now recall that Y is M1 of N. So for each gamma 1 of N conjugacy class P prime belonging in the conjugacy class of P, you have the unipotent radical of UP prime that is mapping modulo the intersection of gamma 1 of N with UP prime. That is this is the Serre fibration mapping to the boundary component for P prime, Borel-Serre, mapping to the locally symmetric space for M prime, and this is gamma 1 of N intersected with M prime. This is the level for this S of M prime. And then this maps, this is the boundary of the reductive Borel-Serre, and so this maps to the component of the Bailey-Borel compactification, and this is a it's not exactly equal, but up to a finite map, this is equal to a Shimura variety, the Shimura variety for the Hermitian part of M prime, which in this case where I'm taking inside P, uh, the Hermitian part of the Levy for P prime, which is just a Gn. This is a quotient of MP prime, which is just a Gn. And actually this map, so MP prime is GL2, and this map is induced by determinant. So it's really actually the connected component map. Okay, but all right. So this is the picture for the boundary of components associated to Siegel parabolics. And maybe let me state just another description, is that this quotient is just S1 topologically, S1 times S1 times S1, because UP prime is a billion. Okay. So it's R3 modularis. Okay. So this is the picture. And so this is for a given component associated to a parabolic, but now you want to compute the cohomology of the full boundary. In general, there is a spectral sequence for each boundary component, but in this Q rank 2 case, the spectral sequence, so there is a long exact sequence, it's just a long exact sequence. So here you have the cohomology of the full boundary, so those composed of all the components, mapping to only the ones with respect to P plus the one with respect to Q. So these are the maximal parabolics mapping to the one of the minimal, so the Borel one. Okay, so with this exact sequence, you can study the cohomology of the full boundary. Okay, so this is a rather technical subject. I'm doing my best to present a lot of content, but so these are the main ingredients. So these four compactifications with this description of their cohomologies. And so actually the key from a representation theoretic point of view is the following, is that you can compute the cohomology of each boundary component. So this I'm taking the limit over all levels, so that everything has an admissible GAF action. So the cohomology of this, you can describe as a GAF module as an induced representation. So the finite at L to the to GOF. And so here I have something that depends on Val group elements. These are the same Val group elements that appear in the computation of the constant term of Eisenstein series. Obviously, it's not a coincidence of, well, the cohomology L of W is the length of the symmetric space for MP with coefficients in some sheaf. I will not say what this sheaf is. It depends on the length of, it depends on who W is. Okay, but the upshot is that the cohomology of the boundary is an induced representation. Induced from what? Well, from a representation of the levy of P that is given by the cohomology of the local symmetric space coming from the levy of P. Okay, so this is sort of the key description to study how this Eisenstein class behaves in cohomology. Okay. Okay, so I finally arrived at my number 3, which is the description of the Manin-Drinfeld principle. Actually, before I start talking about the Manin-Drinfeld principle, are there maybe any questions about at least the general setup?
Hang on, there is one question. 1 minute.
Yeah.
Sorry, I want to know how is the retraction done for the Borel sphere?
Ah, yes. So it
retracts to the cusp at infinity. You're compactifying by putting a circle at each cusp, right?
yes.
So I'm slightly confused how it retracts.
So it's so there is this. So you retract along geodesics. So if you want from the okay, so maybe let me uh, check this. So if here I have the upper half plane, and so here I have my interval from say 0 to 1 for gamma 1. So each point here, the boundary you should it's like so you're going to the boundary. So if here I have a point z, you're going to the boundary by taking tz, where t. So now uh, t is real. Sorry, t squared z is real, wherein the absolute value of t goes to plus infinity. So this is sort of saying that you're shooting a geodesic up in the air, and at the boundary, you will see that each point of the circle, so this point is identified with this point, but so you see you will draw for each geodesic, the point at infinity will come down to this guy. So I mean, sorry, I'm explaining this very poorly, but the key, this is the geodesic retraction. So you're retracting along geodesics, and it comes really from the definition of the Borel-Serre compactification, where you're going at infinity along geodesics. And so the boundary is all the limit points at infinity. And so going back, it retracts.
Okay, look, explanation looks good.
Okay. So yeah, so if you want a reference for this is Harder. All the papers of Harder do this in quite some detail. So Gunther Harder. Papers that study this Eisenstein cohomology business in quite some detail. Yeah, and the paper I'm most familiar with is the one with Goreski and McPherson, which is called weighted cohomology. Okay. Yeah, sorry for the sloppy explanation. Okay, so now let me go on to the Manin-Drinfeld principle. So the key, as I said before, is that you have this this exact sequence, the cohomology with compact support with coefficients in C, with y and coefficients in C, to the cohomology of the boundary with coefficients in C. And again, here I'm taking limit over all levels, so that on this sequence there is an admissible GAF action. So now the image of compact support cohomology in the cohomology is known as the interior cohomology. So H dot of YC goes to H dot of delta Borel C. So this is the image of the compactly supported cohomology. So you have this exact sequence, but the key point is that the interior cohomology lies in L2 cohomology. This is L2 cohomology, as defined, say, by Franke, L2 cohomology. But this the GAF action is unitary. There is a natural L2 pairing on the L2 and on the L2 cohomology. And what the Manning-Drinfeld principle states that pi chi, the finite part of pi chi, does not appear as a representation in the interior cohomology. So, and what is the proof of this? Well, because pi chi finite is not unitarizable. So when chi is not even quadratic, this is obvious because pi chi is not even Hermitian. So it can possibly be unitary. So this is only a problem when P is 3, where we want to take the Teichmüller character, which is quadratic. But if it is quadratic, there are also other arguments that lead to the same conclusion that pi chi is not unitarizable, which can be proven, say, by computing the constant term along the Klingen parabolic, which is a GL2 Eisenstein series of width 3. I will not give this argument because in the case where chi is not quadratic, which is almost always the case except when P is 3, then this is obviously not unitarizable. Okay, and in the case of GL2, you can even use a softer argument. In the case of GL2, the Manning-Drinfeld comes from, say that the Eisenstein-Heck-Hagen system is too big in absolute value. Large to be ever be cuspidal. So because in the GL2 case, the interior is just the cuspidal part. Plus the trivial representation, but okay. So this in Chris's lecture, the Heck-Hagen system was 1 plus chi LL, and the trivial bound on Fourier coefficients of GL2 modular forms say that this is not possible. Okay, so the Manning-Drinfeld principle says that this representation of GAF does not appear in the interior cohomology, and so this means that once you take pi chi infinity isotypical components, well, this needs to be injective when restricted to the boundary. So this is the statement is that so consequence is that this map is in the deck chain. So this is the restriction to the boundary. It's just pullback. And by the long exact sequence computing the cohomology of the full boundary of the Borel-Star compactification in terms of each component, you can actually show that even when you compose with the restriction onto the boundary component indexed by P, this is also injective. So this is a geometric statement, avatar of the statement that the Eisenstein series are determined by their constant terms. So this says more is that the properties of omega chi, which lies in H3 YC, are determined by its image in H3 of P delta Borel-Serre. C. But what is this image? But omega chi maps to its constant term along P. And this is explicitly, which will give you an element of the H3 of the P boundary component of the Borel-Serre compactification. So this says that omega chi inherits the rationality properties of its constant term along P. And a small study of what the rational structure of this cohomology is will tell you that actually omega chi belongs to the H3 of Y with coefficient in Q chi, where Q chi is the field obtained by adjoining the values of chi. So let me maybe state how this works in the GL2 case by referencing Chris's talk. So we had our differential f of chi tau d tau, but when you go to the boundary, so you have f of chi t tau d tau, and so t is a real parameter, sorry, t squared, and the absolute value of t is going to plus infinity. So this differential, so this is the action t inverse, this differential, this quantity converges to the constant term at infinity, okay? So let me do just the constant term at infinity. And this d tau, so if tau is x plus iy, on the boundary, which is inside P1 of Q, which is inside P1R, if I see this inside the compact dual, P1 of C, then the limit of this, as t goes to plus infinity, will be constant term times dx, where dx is just the one form on R mod z, which is the circle that you have attached at the infinity cusp. But obviously the period of dx on R mod z is rational. So it's a rational basis of the cohomology of the circle. And so you see that f of chi of tau d tau inherits the rationality properties of the constant term. Okay, this I've only done the computation at infinity, but obviously at other cusp is the same. Okay, so this was the GL2 case. All right, and so now I just have to conclude by how do you define the étale class? Well, now for simplicity, just for simplicity, we assume that chi takes values in mu p minus 1, which I see inside of zp. Chi is valued. So this is just not to worry about what kind of coefficients I need to take. So then we have omega chi, which define a singular étale class in Y Q chi. But so this is Betty or singular. And so this, by Artin's isomorphism, is also tensored with over Q. So tensored with QP is it's also H3 et al. Of Y of QP. So you look omega chi et al. Is just the image of omega chi tensor 1 on the Artin's isomorphism. Okay, this is my et al. Class. So this is the et al. Class. That in Chris's talk, he also denoted it by omega chi et al. And it's the key to constructing the Euler system is this et al. Class. And so now we want to understand the Galois action on omega chi et al. And this is done in two steps. First, show that, so if iota BB denotes the inclusion of Y inside its Bailey-Borel compactification, then you want to show that omega chi et al. Actually defines a section on YBB of R3 iota BB star of QP. And the key in doing this is that there are theorems of Pink gives an explicit description, a representation theoretic description, and what the Galois action on this sheaf is of Ri iota BB star QP restricted to a boundary component. So delta star of the Bailey-Borel compactification. So this is a result of Pink that trace formula people, for example, use a lot when they're working with non-compact Seymour varieties. So first you see that omega chi et al. Is the global section of this sheaf, and now you argue as before. So you say that because of some version of the Manin-Dreamfield principle, also in this case, omega chi et al. So the map H0 of YBB R3 iota BB star QP star, when you restrict to the cohomology of the boundary component indexed by P of the Bailey-Borel compactification, and now here the sheaf restricted to this boundary component. These are just points. You have one point for each connected component of the locally symmetric space for the GL2 that appears in the levy of the Ziegel parabolic. So this is also injective when you consider pi chi f isotypical components. And so the Galois action, so here you have your omega chi et al., which belongs here. And so the Galois action on this class is determined by the Galois action on its image in this boundary. But the boundary, these are just points, it's just a Seymour variety for GM, so the Galois action on this variety is completely explicit and easy to understand. And so you will see that GQ acts by a character on omega chi et al. And you can see that this character is actually, it's actually chi inverse epsilon minus 3. Epsilon sig is the cyclotomic character. Okay, so it's really the key in understanding the Galois action on this class and the rationality properties, which allows you to even construct the étale class is this Manin-Drinfeld principle, which comes from the fact that philosophically, that Eisenstein series are entirely determined by their constant term, but this is true analytically, but it's also true sort of geometrically in good situation. So let me just say that next time, if you want to stick around, we will talk about how to upgrade QP with ZP. It will be the most technical part of this lecture series. All right, so thank you for your attention. I think I'll stop here.
Any questions or comments?
Hi, can you hear me?
Yeah, hi.
Okay, so I wanted to ask, you also have the framework like you have reductive group G and H as a subgroup. The Shimura variety of H goes to Shimura variety of G. So the low-flux norm compatibility machine also have the same framework. But in his framework, he also have some conditions on the Levy subgroups and the parabolic subgroups. Do you also have those kind of assumptions? Like you consider some spatial element U and U inverse and
So this is already in the construction of the Euler system. Because my understanding of what they do is that they assume that the classes on the small group verify some norm compatibility, and then they find some way of pushing them forward to the big variety in such a way that they are norm compatible. But so this is already inside the construction of the Euler system. But in this talk, there is no H. So
yeah. I was like referring to last talk as well. So
oh, last talk. Okay. Then last talk. No, it's not. It's not yet clear to me in this pullback situation whether there is such a procedure that seems to axiomatically work, because you have to. It's very related to what kind of sections at P you choose for your Eisenstein series. Here I gave a very simple one, but it's not the correct one if you want to get the norm relations at P. You have to modify your Eisenstein series, a little bit like Chris did with his Atkin-Lehner involution. But so you have to modify your sections at P, and you have to choose the sections at P that the people who construct the p-adical function chose, so that you have your explicit reciprocity law that matches with the p-adical function. And so that is the guiding principle for how you should prove the norm relations at P. It should be guided by what kind of sections at P are chosen in the construction of the p-adical function. So so I would say no, there is no axiomatic sort of way, or at least we haven't developed one, to get the norm relations at P automatically.
okay, thank you. And one naive question. So if you don't have étale cohomology in the Bianchi modulo forms case or Bianchi threefold, is there any way using your new framework to construct some Euler system there?
No, so the idea would be something like lifting the representation to somewhere that does have a Galois action. But yeah, no, it's really necessary to realize or whatever the Galois representation you're considering in cohomology. Yeah.
Thank you.
Hi, like just for the today's construction on the construction of the like this Diram class and the abelian nature of the Galois action, is this something one expects in quite general situation?
So definitely when the series is induced from a character, when there is no higher dimensional representation you're inducing from, so say that there is no actual hospital part, it's just a character, then yes, I think you expect this under the Manin-Drinfeld principle. At the trivial character or quadratic character, something weird can happen with with cap forms, maybe there's an extension there. So the Galois action isn't abelian, but I don't have any example where this happens. But yes, definitely if the Eisenstein series is degenerate, I would say yes, it's a general expectation. And otherwise, no, the Galois action should be more complicated if you're inducing from something more complicated than a character.
Any more questions or comments? If not, let's thank Marco again for his nice talk.
Thank you.